Okay, students, let's do our lecture video on rotational motion, and I'm going to try to keep it short and sweet. Just kind of hit the highlights. I'm going to try to keep it to 30 minutes, so let's get started. All right, so when we look at rotational motion, most all of you have, I hope you have, at least sometime in your life, have used a wrench. Actually, if you've ever turned a doorknob, then of course you are using something called torque. Now here they show us how to loosen a bolt, and of course common sense is going to tell us that we need to apply our force where? The easiest way to loosen this bolt would be to apply our force here, wouldn't it? Absolutely. Well, why? Because we're not going to get as much torque because the radius at which the force is applied to the axis of rotation is much smaller. So again, common sense is going to tell us that we want to use a longer, what we call lever arm. Now, some of you, especially if you've been in a mechanic or done construction, you know you can come in here and put a pipe on the end of this thing called a cheater and increase the amount of torque. So that's why we do that. So what is torque? Well, there's a couple of things you need to understand about torque. There's something called the line of action, which is basically the force that is along, the line of action force is the line along which the force vector lies. So in other words, if you see right here, all right, let's say we're applying a force right here at this point, you can see the line of action force is in that direction, okay, because he's pulling in that direction. Of course, it's perpendicular to the actual lever arm, okay, which is very important because if you want to get maximum torque, then your line of action has to be perpendicular to your lever arm. Now the lever arm, of course, is what? It's the force perpendicular, is perpendicular to the distance from O, all right? So what is O? Well, O is the actual point at which rotation occurs, okay? That's your point of rotation, okay? So that would be your bolt if you were trying to remove a bolt, or that would be the center of the doorknob if you're turning the doorknob. You know, you have a lever on a door closure and you touch the end of the lever. You don't grab it up right in the center of the lever. It's a lot harder to turn, isn't it? Well, that's why, okay? All right, so here we see three ways to calculate torque. You can calculate it this way, right here, using, if you look at the tangential torque, it's tangent to the line of action. It's tangent to the point of the line of action right here. So you can say basically what? You can use the force applied times sine of the angle. Sine of the angle. Remember why sine of the angle? Because it's opposite over hypotenuse. Or you can look at it using the radial force and take the cosine of the angle adjacent over hypotenuse, okay? All right. So it'd be F cosine theta. Or you can just say what? There's a couple of different ways. Notice you can say the force times the length, R force RF sine theta, or phi, or just what? The force tangent times R. Now, how do we find L? If you ever see the symbol L in there, well, L is simply found by using what? R sine theta, okay? And of course, L equals the lever arm, okay? So R sine theta is L, all right? Now, so that's three different ways you can calculate torque. It might not hurt to put those on your formula card. So, torque, we need to understand it is a vector because direction does matter, okay? So here's an equation we need to add to our formula card. Torque, tau, that's the Greek letter tau, is actually the cross product of what? Or the vector product, if you want to look at it that way. You can say it either way. The radius, and that's the distance from the point of motion, your axis of rotation, to where the torque is applied, okay? All right, so the radius times the what? The force vector. And this is a vector product because why? Because direction does matter. Now notice if the rotation is counterclockwise, you have positive torque, and if it's clockwise, you have negative torque. Why? Because if you think about it, if you remember your angles, when you move counterclockwise, that is positive, that is increasing displacement or increasing angular displacement, okay? So if it's increasing, it's positive. If it's decreasing, it's negative, all right? So when we look at angular acceleration, here they show you using a screwdriver to tighten or loosen that screw on that switch cover. The sum of all the torques is actually equal to the moment of inertia times the angular acceleration of the rigid body, okay? So, and you say, well, where does this moment of inertia come from? Well, here it all depends on the shape and the dimensions, the characteristics, I guess you could say, of your rigid body. And where do you get that? If you go back, and I believe in chapter 9, there were like 12 different equations to find the moment of inertia. So you have to use the correct equation based on, let me see real quick, that was on page, if I can find it really quick. I guess I should have already had it written down. It's in chapter 9. Yeah, page 286, table 9.2. So I think there were, I said 12, there's 1, 2, 3, 4, there's 4, 5, 6, 7, 8, 9 different shapes, okay? So again, that's what our moment of inertia will be based on the type, the shape of the rigid body about which is being turned, okay? All right. So when we look at external torques, now it's very important to understand that if you do not have any external torque on a body, then there is no net torque. And you say, now what does that mean? Now basically that's what this is trying to demonstrate, just showing you how you can have different torques on an object. And if the forces are the same and the radius from each, then if the radii are the same, then guess what? You have no net torque. Well, what do you mean? Well, think about it this way. If you have a seesaw, folks, and you've got an object here and an object here, and the masses of one is equal to the mass of 2, 1 and 2, well, guess what? There's no net torque, okay? There's no net torque, and the seesaw should just set level, provided your fulcrum is right in the center, okay? That's very, very important, isn't it, okay? Because you got to remember now, the radii have to be the same. So if you have, if the forces acting on a body are the same, they're equal in opposite direction, then there's no net torque, right? Okay. So how do we do rotational dynamics? Well, and this is good. This is in your text. Let's see here. I'm trying to remember what page this is on. I think you begin to see this on pages, I think it's 308 and 309, okay? But anyway, this is a good problem-solving strategy to do torque problems. Of course, you set it up with the following. You always have to sketch it, all right? You always have to sketch the bodies that you're looking at. And you always need to indicate the axis of rotation. And then, of course, you need to draw a free body diagram, label all your angles, choose your coordinate axis, and determine which is counterclockwise, clockwise, and counterclockwise. Okay, it's very important. And then determine your z-axis, and then of course execute the solution as follows. All right, determine whether it goes through translational motion, rotational motion, or both. Remember, translational is like moving in a straight line, and then of course rotational motion is going in a circle, okay, or moving through an arc, okay. Okay, and then of course you express the algebraic sum of the relationships, and then of course you need to ensure that you have as many independent equations as there are unknowns, okay? All right, so that's very, very important. Then of course you always evaluate your answer. Now, what about a rigid body rotating about a moving axis? Now, if you remember when we did our chapter on work, I think it was chapters, 5, 6, 7, we talk about work and energy. Remember that work, of course, is equal to what? It's the integral of the force dx, isn't it, right? And if force is constant, then we can actually say what? We can solve it this way, the force times the change in displacement, can't we? We can do it that way. All right? So just remember, this is a scalar quantity. Remember that energy is a scalar quantity. Very, very important to remember that the direction of the work, that we don't worry about the direction of the force. Even though force is a vector, it is a vector quantity, work is a scalar quantity, okay? And when we start looking at positive and negative with work, remember it just has to do with whether work's being added or work's being taken away, all right? So direction is not important because work is a scalar quantity. Well, same thing with kinetic energy, because kinetic energy you need to remember, is equal to work, okay? It is equal to work. So how do we calculate then the kinetic energy of a rotating body? We have to look at both. Now, we've already discussed center of mass back, I believe, in chapter 9. And so we have to look at the energy of the total mass of the system about the center of mass, and then we have to look at what? We have to look at how much energy is being created by the moment of inertia, okay, about the center of mass. Notice this one deals with the velocity center of mass, and this one deals with the angular velocities about the center of mass. So you have to look not only at translational, but you also have to include rotational. Now this is the total energy. If we wanted to know the total energy of a body in motion, this is how we would calculate it, okay? So here's your equation. That's the total energy, okay? The total energy, very important. Now again, you can see that there's translational. What do you mean by translational? Notice that the object is moving from here to here, and rotational, notice that it is spinning, okay? So in other words, if I were to take this baton and twirl it and throw it up at an arc, then it's going to have both translational, okay? Here's the translational aspect of it, and here's the rotational aspect of it. If I took a baton and I spun it and threw it up at the same time at an angle, it's going to have both, okay? All right, now what about rolling without slipping? Well, that's very easily calculated. If we want to look at the velocity center of mass of an object like a tire, say a tire rolling down the street on your car, because it's not slipping. You don't want it slipping because you're wasting energy and you're not getting anywhere. That's why when we have anti-lock brakes, we don't want to go into a skid, because skidding produces acceleration, and when you want to stop, you don't want to accelerate during stopping. You're wanting to decrease acceleration, aren't you? You want to slow down. So how do we find the velocity center of mass? Here's another equation you can add to your formula card. We basically look at the radius times the what? The angular velocity. That omega, if you remember from the previous chapter, is angular velocity. It's very simple to calculate, okay? All right, so let's continue on down. Let's look at combined translational and rotational dynamics. So when we look at the acceleration about the center of a mass of a rigid body, notice that the net external force is equal to, when we say that, that's the sum of all forces externally, is equal to this is about a rigid body now, the total mass times the acceleration at the center of mass, okay? In other words, translationally. Then when we want to look at, and this would be considered translational, then when we want to look at about the rotation about the center of mass, dealing with Newton's second law, then we look at what? We look at the sum of all torques is equal to the moment of inertia, center of mass, times the what? The angular acceleration. Now remember, right here, your moment of inertia will be dependent on the actual material that is in rotation. I mean, if it's a rod, if it's a hollow tube, if it's a solid sphere, if it's a hollow sphere, I mean, you have to go and look at those equations in chapter 9, okay? All right. And of course, we know this is in newtons, and this answer here should be Newton meters, okay? Newton meters. Now, what about work in rotational motion? Now, we've already looked at the total kinetic energy, translationally and rotationally put together. Total, we put them both together, translational and rotational. Now, what about when we look at work? Well, if we have a tangential force applied to a rotating body, guess what? It does work on it, doesn't it? Well, sure, it has to. You say, well, how do you know that? Well, look, here we have torque, and here we have changing, the angle is changing. You could also write it this way. Work is equal to the torque times a change in theta, which is the angle. You could write it that way if you didn't want to integrate it. Let's say, for example, the torque is constant, all right? We could write it that way, all right? Now, so here they use the example of a merry-go-round, and they show you a tangential force applied about a radius, and it's moving through an arc. So we can find out how much work, again, a scalar quantity. Always remember, work and energy is a scalar quantity. It's not a vector quantity, okay? All right, so we can look at then what? If we integrate the the changing in the angle, if we take the upper limit to be the final angle minus the lower angle or the initial angle, then we do what? We multiply the torque times the change in angle, don't we? Okay, so it's basically what this represents. You know that changing theta is delta theta. And of course, if we integrate it, we have to have a function to integrate, and we integrate it with respect to that, all right? But if it's constant, we can do it algebraically real easy, okay? So again, the total work is equal to what? The torque through the changing angle, or multiplied by the change in the angle, change in arc, okay? Well, what about power? Power, we know that what? Power, if you look at it in Newtonian, well, we're still really in Newtonian, but if you go back and look at it when we're looking at work, remember power is the work divided by the time, isn't it? In other words, it's the rate at which we use energy, isn't it? It's the rate at which we use energy. Well, power due to a torque can be calculated simply by multiplying the torque times the angular velocity of the object. And yes, we will still get the units of watts. Remember that power is always in watts, okay? Power is in watts. So please remember how to calculate that. And then we look at angular momentum. Now, angular momentum is interesting because it's basically derived from, I didn't mean to do that. If you remember translational momentum, which is the mass times the velocity of an object, the product of an object's mass times the velocity, and by the way, it is a vector quantity. It is a vector quantity. Need to remember that. It's a vector quantity, and angular momentum is also a vector quantity too. Then if we come in and if you remember our equation, now look, to find the angular momentum, we can write the equation this way. We can say the length of the angular momentum is equal to the mass of the object times the velocity of the object, okay, which is important. Let's say it's here, but now remember, if this is connected here and it's moving in this direction, look, we've got a radii, don't we? We sure do. We've got a radius, okay? We've got a radius. Does that make sense? Instead of just it being a linear momentum, now we've got momentum. We've got an object attached here at point O by an arm, and it has a length of r. Then it becomes what? mvr, doesn't it? We can find angular momentum that way. But since it's moving and it has an angular movement, then if you remember that the velocity is equal to what? R omega, right? R omega, the radius times the angular velocity, and I believe that was velocity center of mass, but either way, it'll still work. Then we can substitute, can't we? We substitute right here, and we have m what? We have m, and substitute for v. We've got m times r times omega times r, or we can combine those two r's together and it becomes r squared. And so we can find the angular momentum simply by taking the mass of the object times the radius squared times the angular frequency. There's another formula to put on your formula card and give us the angular momentum. Very simple to calculate. We can also, yes, some of you probably already thinking ahead, we don't have to have the mass times, well, we will end up needing the mass, but we can calculate the angular momentum of a rigid body rotating about a symmetry axis by doing what? Taking the moment of inertia times what? Times the moment of inertia times the angular frequency, okay? Excuse me, angular velocity. I had a mental lapse there for some crazy reason, okay? All right, so again, here you have to remember your equations. If you remember your equations from moment of inertia, you said, where does that come in? Well, go back and look. It was mass times r, wasn't it? Well, if you go back and look at our equation, we see that right here in our equation, don't we? Sure we do, okay? Mass times r, yeah, it's right there, okay. All right, so the moment of inertia times the angular velocity. And then, of course, if we're looking at a system of particles, and we're looking at all the torque, then all the torque, the sum of all the torques, and that's what that Greek letter sigma means, the sum of all torques, can be calculated by finding the what? By looking at the rate of change in the angular momentum. In other words, how much is angular momentum changing during a time interval? Of course, we know that's a differential equation there, isn't it? Okay. All right, now, so angular momentum, how do we determine if it's positive or negative? All right, if the angular momentum is counterclockwise, or excuse me, if the angular velocity is counterclockwise, notice you take your right hand and you cup your fingers in the direction of rotation. Notice it's moving counterclockwise. That is positive, remember, go back to chapter 9. That is positive angular velocity. Then guess what? The angular velocity and the angular momentum are in the same direction, aren't they? They sure are, okay? Okay. But if you flip it over and you make the velocity go clockwise, then notice what happens. Your angular momentum and your angular velocity is negative, okay? So we use the right-hand rule, and that's how we do it, okay? All right, now, this will be our last slide. When we look at the conservation of angular momentum, if you've ever, done this, or you've probably seen your high school instructor do this, I reckon that's supposed to be Einstein. I don't know. I sure don't look like that anyway. And you've probably seen ballerinas. You've probably seen figure skaters. And basically what they're trying to get you to understand here, that when you have no external net torque acting on a system, then when there's no external torque on the system, the sum of all the torque should be equal to 0. Now, it doesn't mean there's not torque. It just means that there's not any net torque, okay? For example, you have the professor here. He's on a stool, and he starts himself spinning, and he's holding the dumbbells out perpendicular to his body, okay? You've all seen this demonstrated. You've all seen a figure skater do this. Then they're turning, aren't they? And they spin and they spin. But then when he starts to pull them in, guess what happens? Well, he speeds up, doesn't he? Well, how does he speed up when there's no net external torque? The sum of all the torques are equal to 0. Well, you got to remember that the angular momentum is equal to what? The mass times the it's mass times the velocity, r, or it's what? It is the mass times the angular velocity, r squared, isn't it? Right? That's two ways we can write it, okay? Now look, if you think about it, if you look and you say, well, what happens to velocity? Well, if you solve it for velocity, watch what happens. That's constant, but r. If r is changing, look, if r goes down, if r gets shorter, then guess what happens to your velocity? You speed up, okay? So the reason you see a figure skater speed up when they bring their arms in, it's not because there's a net torque. It's not because someone's magically, there's an invisible person out there, spinning them. Of course not. We know that. It's because that they are changing the radii by bringing their arms, and they're causing all the mass to come to the center of their body, or as close to the center of body as possible. So guess what? If you shorten that radii, you increase the velocity, okay? All right, I hope this little quick lecture helps.